What if one model could understand an image, generate a masterpiece from a prompt, and edit it with precision, all in a single unified architecture? This isn't science fiction. It's Emma, efficient multimodal understanding, generation, and editing with a unified architecture. And today, we're diving deep into how Emma redefines the frontier of multimodal AI, efficiency, performance, and generalization, without sacrificing any of the power. At its heart, Emma tackles a fundamental challenge in unified multimodal models, the imbalance between understanding and generation. Most systems use different compression ratios for visual encoding, say 8x for generation, but 32x for understanding. This mismatch forces models to work with mismatched token counts, creating bottlenecks and inefficiencies. Emma solves this by introducing a 32x compression autoencoder, a high-efficiency deep compression autoencoder, or DCAE, used consistently across both the understanding and generation branches. That means a 1024 times 1024 image is compressed down to just 1024 visual tokens, no matter whether it's being analyzed or used to generate a new image. This alignment ensures training balance, so the model doesn't favor one task over another. But here's the real innovation: channel-wise concatenation. Instead of merging visual tokens token by token, a method that inflates context length, Emma concatenates them along the channel dimension. This means the semantic richness from the understanding encoder is fused with the high-frequency detail from the generation encoder. But the total number of visual tokens stays unchanged. The result? Up to 5x fewer visual tokens in image editing tasks, without losing performance. This isn't just optimization. It's architectural elegance. Now let's talk about how Emma handles the dual nature of multimodal tasks. Understanding requires deep semantics, while generation needs fine-grained detail. The solution? A shared-and-decoupled network architecture, a design that's both collaborative and specialized. In the shallow layers, Emma shares parameters. This allows the model to learn universal visual patterns, edges, textures, object shapes, across tasks. But in the deeper layers, it decouples. Why? Because understanding and generation have different modeling needs. The understanding branch focuses on what the image is. The generation branch focuses on how it should be rendered, down to lighting, texture, and stroke. So Emma shares early features, but diverges later, ensuring mutual improvement while preserving task-specific fidelity. And this isn't just theory. It's proven. Emma achieves state-of-the-art performance on benchmarks like MMVet and GenEval, despite being built on a 4B LLM, outperforming even larger 7B models like Bagel. But here's where Emma gets even smarter. Multimodal understanding isn't one-size-fits-all. STEM images, scientific diagrams, equations, schematics, require a different kind of perception than general images. So Emma extends its vision encoder with a mixture of experts, MOE mechanism, inspired by Mixpert. It introduces a dedicated STEM expert, a specialized module trained to handle technical visuals. A router dynamically routes each image. If it's a scientific diagram, it goes to the STEM expert. Otherwise, it flows through the general versatile expert. And here's the kicker. Only tilde 50 million additional parameters are added. The STEM expert is trained only in the final tuning phase, using 15 million STEM-specific data points. Yet this tiny addition boosts performance on multimodal understanding benchmarks by 0.4% on average, across 11 datasets. And crucially, it doesn't degrade generation or editing quality. This is efficiency and specialization in one compact design. But how do you train a model like this? Emma's training is a carefully orchestrated sequence. 1. Alignment frees all components. Only fine-tune the understanding adapter to align visual tokens with the LLM. 2. Pre-training, train everything except the DCAE. Use a 1-1 balance of understanding and generation data. 3. Supervised fine-tuning, now train with native resolution inputs. For understanding, use real image sizes. For generation, scale to 1K resolution. Balanced sampling ensures diversity. 4. Quality tuning, jointly train all 3 tasks, understanding, generation, editing with a 1-1 batch ratio. 5. STEM and router tuning. Finally, train only the MOE components, using specialized STEM and routing data. This staged approach prevents catastrophic forgetting and ensures robustness. Let's look at the results. On multimodal understanding, Emma B achieves 85.8 on MMVet, a 5.8% improvement over Bagel 7B, while using fewer parameters and less training data. It also outperforms QN3VL by 0.4% and Intern VL35 by 2.6% on average, across 11 benchmarks. On text-to-image generation, Emma scores 0.91 on GenEval, without prompt rewriting or reinforcement learning. That's higher than Bagel 7B, 0.82, and QNImage 0.87, despite having a smaller model. And on image editing, Emma achieves 6.53 on gedit benchen, slightly ahead of Bagel 7B, while using only 1/5 of the visual tokens. This is the power of unified efficiency. But the real magic: Emergent capabilities. Emma was trained on English-only editing data. Yet it natively supports Chinese instructions, just like this. Chinese letter, 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 Chinese letter. Take off the headphones, change the hair to blue, and put on sunglasses. And it follows complex, multi-step edits, even when the training data only included single instruction tasks. Why? Because Emma learned multimodal chain of thought reasoning, enabling it to parse and execute instructions like replace the crab with a frog, change the background to a snow-capped mountain, and add rain. All while preserving character consistency, a rare feat in image editing. And here's a critical insight. Emma excludes the GPT image edit 15M dataset because it harms subject consistency. This isn't just about scores. It's about robustness, reliability, and real-world usability. So what does Emma mean for the future of AI? It proves that efficiency and performance aren't opposites. With a 32x compression ratio, channel-wise fusion, shared-and-decoupled design, and lightweight MOE, Emma achieves 5x reduction in visual tokens, superior performance across understanding, generation, and editing, emergent multilingual and complex instruction capabilities, and scalable end-to-end training with fewer resources. It's not just a model. It's a blueprint for the next generation of unified multimodal systems. If you want to explore the code, training data, or results yourself, visit GitHub.io/Emma. And if you're excited about the future of multimodal AI, this is just the beginning. Because when understanding, generation, and editing are unified, not just in function but in design, the possibilities are limitless.